Coming online. Okay, it says I'm online. Turing Complete Part 4. Okay, where we left off last time, I had completed everything below this line here, which was functions, push and pop, stack and RAM. Okay, I don't need all this. We modified the computer in RAM, push pop and functions. I'm going to redo that, but before I do that, you come back down right to the beginning. Let's start with OR gate, for example. That's an OR gate. However, a quirk of the game is that just doing this counts as an OR gate. If it's off, it's off. But if any input is on, the line is on. So it uses what would be known as a pull down effect, as if there's a resistor between your line and ground which holds it low, but as soon as anything pulls it high, everything goes high. So as an example, this one went high, it's on, it's high. The other one went high, the output's high. So this is an OR gate in the game. So we can now see that our OR gate has a NAND delay of nothing. I don't think we can do anything with NOT, but now that we have an OR gate design that has fewer NANDs, well, oh look, let's do the same thing here. And now we have a NAND score the same as our NOT, because we did things. AND gate, I don't think we can minimize that anymore, because we only have access to NANDs and NOTs, and with NANDs and NOTs, that's about it. We could NOT, then connect, which is an OR, then NOT, but that would have 3 NANDs and a delay of 4, so it'd actually be worse. So there's nothing we can really do to help this one. That doesn't have a score. This one, well, there's not really a lot we can do again because of the thing. It's not that important because it doesn't unlock a component. The main ones we want to try and minimize the score on are the ones that unlock a component, like XOR. And with XOR, I believe this is actually the minimum you can do. However, when we go to XNOR, well, there is actually something else we can do to minimize it. I forgot what it was now. Rather than using an XOR gate, I mean, we can use OR gates. So what we want is an ON here and here, which is both off or both on. I can't remember the answer to it, unfortunately. It's I mean let's go back to XOR, create the full XOR, because I think that was a starting point. It's yeah. Oops. Like that. So one option is to not that, the other one is to not that, which means if we I'm thinking about this the wrong way, I think. I had a solution but I can't remember it, but it would actually make the XNOR faster than the XOR. Anyway, let's go. That's wrong, but let's go back. Create an OR gate. Well, our OR gates cost nothing now, so if we just run it again, it crashed the game. Let's try that again. If we just run it again, yeah, but that unlocks whoops, that unlocks the 3 input AND, which is unlocked here, not the AND, the OR, 3 input OR. Is there an easy way to see it? No, it's difficult to see, but if you look when I point to it, yeah, that's kind of broken because it's not showing up with its... Oh, that one doesn't either. But if you look at the score here on the right, it says NAND score 0, delay score 0, but it also says that under the truth table when you point to it. With a 3 input, for some reason it's not bringing it up here when you select it. But I can see faintly that it says delay 0, NAND 0, so we did reduce the cost. What was the answer to this? It was that, and then I think it was something silly like that. Yeah. So let's just run through that again. So we turn it on for get the first one. When they're both off, you get a 0. And NAND only turns on when... Okay, only turns off when they're both true, which means... Stop. For the first step, it only turns off when they're both on, and since this one's off, it's off. So now it turns on, so they're both on, because yeah, it only turns off when they're both on. They're both on. And then likewise with only one, they're both on, because that turns on when either of them are on, and that only turns off when they're both on. And then the final one, well, they're both on, so that's on and that's off because it's only off when they're both on. And yeah, only one of them's on, so it's on. So yeah, so our XNOR now has, that's as far as I can zoom in, our XNOR has a NAND of 2 and a delay of 4, where our XOR has a NAND of 4 and a delay of 6. So our XNOR gate is faster than our XOR gate, Unfortunately, we can't improve our XOR function by using XNORs, because when you add a not on the end, it basically ends up the same. Hello, Robert. I can't pronounce your surname there, but hello, I do see you there in chat. Odd number of signals. Right. So, this one uses 3 XORs. And as described, our XNOR is now faster than our XOR. So, if we do that, well, that one's off when it should be on. And then we do that one, and it's off when it should be on. So, we've basically just swapped these around so that the offs are ons and the ons are offs, and with an XOR gate, well, when you have 2 offs, it gives the same result as 2 ons. When you've only got 1 on and 1 off, doesn't matter which way around it is, it gives you a high output. So by doing that, we've just cut our NAND score and delay down and should get the same result. Yeah, because these, some of them seem to update automatically, some of them don't. So this one, the sock folding machine, well, just running it again will improve the score. I don't think I did the NOR gate. Which one's the NOR gate? Oh, I did do the NOR gate. But that's important for when we come up here. Which one is the flip-flop? This one, I think. We're not going to change the circuit, but rerunning it should re-unlock that. And now, as you can see, the delay is 2, which is the delay of our NOR gate. So in theory, when we run this one, it reduces the score, but it didn't. That must be one that it automatically recalculated. This is just XOR again. So yeah, most of what I'm going to be doing at the start of this video is just this stream is going through these. Now a lot of them, I already did this one, will just be me pressing play and recalculating the end result, but some of them will need to change. Looks like I did that one. Counting signals. Yeah, this is the one I thought went in. Okay. Again, this bit I can simplify like that. But I don't think there's any other way to reduce the score. I did half adder, I want full adder. Right. Since we're doing this method rather than the other method where we only have 2 ANDs, one taken from this point, I didn't mean to actually click it, we don't care exactly what that signal is. So by replacing the XORs with our cheaper XNORs, we reduce the delay of the adder. However, if I hold, see, I've been having a copy paste issue before. If I do that, press Ctrl C and Ctrl V, nothing happens. But if I instead use the select method by holding Shift and drag, then copy and paste, it does actually copy and paste. And then if I now go into another level, which is adding bytes. Instead of doing that, I can paste in this, which will need a little bit of shuffling and the like to minimize it, because if I'm going to paste this 8 times, I want it as small as possible. Like that, maybe. It's a fairly large level. So one, that's one, and one, and one. This is two there, and this is three there. Then this is our add, that's our carry. And what we want to do is clear all of this, select this. I'm going to move it, yeah, zooming, deselected it. I'm going to select this, move it up here, yeah, with a, oops, with a slight gap at the top, copy, paste. Two. Actually, I can make it even smaller, which I think I'm going to need to do. Because if I select that, I can pull it down one, which means I can. Which means I can now push it a little higher. Where did that one go? Did that reroute? Yeah, it's going that way. Yeah, so that means I can go even higher. What happened? Yeah, okay. Copy. I want to go. That's 1, 2, 3, 4, 5, 6, 7, 8. So I can actually come one down like that. So there's a gap of one all the way around. The result is simple enough because it's just that pin to there on each of them. To there. Carry goes on the last one. Then we want to connect it from there to any of them really, so the top one's easiest. And the first one is the carry in. Then for the others, that's not the first one, is it? That's the second one. And oops, 3 input OR gate there. Right, that's the first one. So then this goes to the second one, which is the top of the XNOR gate. Is that right? That's better. And then the second set here goes to the second pin of the XNOR gate. Right. There. That should be everything connected. And this, look at that delay score, 32. If we have a delay score of less than 40, we get an achievement. So if I press play now, we end up with a NAND score of 80, a delay score of 32, and an achievement unlock. If I do this, can you see it? No, you can't. No, we just unlocked an achievement called Fast Adder. Complete the fast byte adder, which is that level, with a delay of 40 or less. I've had a full adder, and this one, have we done counting signals? I think we did, didn't we? Yeah, we replaced it with XNORs. Got an email, a YouTube email saying that I am now live. Yeah, I know I'm live. I'm just going to close the email program. Thanks, YouTube, emailing me to tell me that I'm live. We did that one. Switch. Well, it's a bunch of AND gates. We didn't improve AND, so this is going to give the same result. Byte not. Yeah. This one, byte or. So, yeah, this should give us a score of zeros. Did switch. I did these two. Input selector. Can't improve it. I don't think it's saving bytes. Again, it's just several of them. I'm not taking note of the numbers before I go in, but this one looks like a big one. 248 and 162. And as you can see, it's already dropped significantly in the corner to 88 and 34. So by invert and add one is how you turn it into a negative number. So yeah, that all I did was go in, press play. It significantly reduced the cost. What's this one? Oh, demux. Yeah. Binary decoder. Yeah, there's not much I can do with that one. Yeah, so this level starts with 2. Okay. Now if I replace that with an OR gate, our NAND score and delay is now 0. So we now have a 0 delay buffer. Little box. I'm not going to mess with it, just delay 50 on this one. that didn't improve. Did I? I think I did binary decoder. Signed. Yeah, signed negate. I did that. I think I've done everything below that line. So this is all just creating things for the overcheck computer, I think. So I don't really want to change anything, just redo the scores. Right, and we don't actually want to do anything with the changing the computer, so we'll just go straight into running the first program, which we broke our leg. We've got two components named cond, two components named ALU, two named deck, leg ALU, leg if, RAM controller. So we want register plus. Oh yeah, that bottom one's just a join. It probably duplicated those others since we redid the levels that unlocked them. See that the NAND score and delay's gone right down from 2K and 550. So we want to do that on every level. But now that we've done that, I need to reconnect these things. Like that. So this is the boring part, I guess, because I'm just doing that. This one. And the maze, and I like to watch the maze, but let's go into the component factory and list these. We have one ALU, one cond. What was the other one? Still listing two on there with very different NAND scores. Yeah. This one does actually take a while to run through. So let's just watch him running the maze inefficiently. Because now a right turn would be useful, so going down this blind alley path. Yep, wrong way. I notice you don't have to actually face the exit to use the exit. You just have to use the exit while you stand there. Press the action button to use the exit when you're standing on the tile in front of it. And that is all of those done. What's next? Architecture 2. By and, well, that one's not going to reduce anything. Byte constant is just that. Not going to reduce anything. XOR. Oh, this is programming an XOR on the overture. Let's go with this one. Byte XOR. Yeah. It's not really going to reduce because we already have the reduced one. Equality. Yeah, just running it's the best we can do on this one, which did reduce it. It's unsigned less. Again, I'm not going to mess with it because it's just too complicated. We could probably reduce this one if we expanded that. What's the delay score? 42. If you take that out, put that there, replace that with a straight through, then add in individual NOT gates. Delay score 40. And the NAND score of only 78. We lost our these are still in there. I want to delete them. How do I delete them? Because they're not actually on the list. But if we add registered duos back in, and those are switch duos. We'll come back to that one later. Actually, so what do I want to do? I'll leave all this wiring in for now, but I want to delete the stack con, the stack, the RAM con and the RAM. That should get our score down considerably for this level. Yeah, the adders are significantly reduced, so our score should be significantly reduced. And again with those pieces missing. Okay, so I could just put RAM back in, but that's not the plan. We disconnect that one for the moment. So I want to group this upwards like that. So what I want to do is, I'm just looking at the things. What I want to do is this mission is to add RAM. So I'm gonna add in custom components, this AD thingy. I put one must be up one there. Right, put another set there. Then I'm gonna get this is a bit of a mess. If I move those, it'll probably cross over other things. But what's this one? We're not. Yeah, let's go in instructions. So stack only cares about that now. Stack. No. Delete stack. Call, pop, and push. If only cares about that now. RAM can go. The ALU only cares about these. And if we go here, right, so I want to delete pop, push, RAM-L, RAM-S, and call. These can remain as they are for now. Where we have reg 0, reg 4, turn that on, and I want to call this one ramad for RAM address, or RAM AD address. Yeah, it's a shorthand one. I know it should have double D, but then also that for RAM. And what I'm going to do is, yeah, I know the program's broken. This one will have the RAM address connected to it. I'm just picking random colours, and this one will have the RAM connected to it. So I need this yellow cable to go there, this one to go here, and this one to go here. I want to move this. So if I just grab all of this, yeah, move it left 3, then grab everything here and then go back right 3. Ideally these that go this way I actually want down here as well, but not important. So now I need to add in some extra, I don't know if 3 would be enough actually, some extra circuitry here where they take this line, take this line as an extra conditional. So if it's if it's let's go with, I really want to delete the extras there, but they don't actually exist. Let's go with component factory. Cond. Game crashed. Yep, there we go. Yeah, RAM is here. And they're gone, that's good. So what I want to do is I want to make a new component. Just a generic one. Oh yeah, component. New one called add_con, the controller for that component. I want to add in we don't need the data bits, we only need a 1-bit in the existing selector, the disable pin, and then disable in, then you want a what do I call it, channel line. Just call it address in, a 1-bit address. But then we want 2 outs, one bit out, yeah. And this is, we'll put the lower ones our disable 0 and disable 1, and we basically want 1 NOT gate and 2 OR gates. I'll put them here because it complains that we need a thingy in. So when the disable, let's move that down slightly, when the disable comes in on either of them, we don't want to address, so we disable both. When this is 1 and a 0 comes in, that's 1, that's 0. When a 0 comes in, we're disabling 0. No, when a 0 comes in, we disable 1 to address 0. When a 1 comes in, disable 0 and address 1. So that's low. That's I want. Yep. So this is our add_con. So now we'll go back to the RAM level, and up here we want 3 add_cons. Let's just push that to one side, put the add_con in there where the bottom one, 0, connects to this first one because we're not multiplying. This is our disable in, and this I'll connect it up later. Oops. This is our disable in, Maybe I should have done that the other way around. And let's move it over there for a moment, because that there. So that's our disable in. So I want this left one more. So if I select all of this, I should be able to go left one. Whoops. Select all of this. Go right one. Yeah. Let's just pull them out so they're that way. This I'll put here. Oops. There. Huh? Ah. I move those. Ah! Like that. So then this one, anyway, to there, there, and there. Right, so now we have a second set of 8 addresses linked up. So this is address 0 to 7 and this is address 8 to 15. And if we look at our, not this one, if we look at our definition, we put RAM address on 12 and the RAM itself on 13. So we want a new, we can edit the existing one because we're not going to use it again, a new RAM controller. We want more than just a RAM controller because it actually wants to contain a memory register. So it's not so much a RAM controller as a RAM addresser. Yeah, we're not going to reuse this. So let's bring this in. It still wants a load and a save. It's going to want, like our opcode. Does it want an opcode? No. Yeah, but it would have been better to start off from the memory duo. In any case, we want IO bit inputs. We want load 1, load 2, save, space, load 1, load 2, save. Byte input is data in. This is, it's got ADR. Oh, ADR load 1, ADR load 2, ADR save, RAM load 1, RAM load 2, RAM save, and data in. So we have save and load out. We're also going to want, let's bring those down a bit. this is RAM, yeah. We're also going to want byte output for RAM address, but we need to be able to access this externally to read the address out. If I return to level and load the code, what we're actually doing is register 0 is our address, so we're saving in to memory location reg 0, incrementing by 1, checking to see if it's less than 32, in which case we repeat. If not, we set it to 0 and start doing outputs, so that's resetting it to 0. So we're basically, if you remember when I first put the RAM, I said I don't want to use a register because that requires writing address then writing a thing, but we're incrementing the counter by 1 anyway, which is to change the address. So we can eliminate that step by having an automatically incrementing RAM address register. So we want an adder with some logic to turn that on. This needs, when save is active. Save is a bit complex because it wants to save when we're also outputting the address. So when RAM load 1 or 2 or RAM save are active, this wants to save because we're adding. So let's add that in. We want an OR here on the loads because that's going to put RAM load, but then we also want an OR from the save because that's going to add and save, as well as switch like that, and this goes to the loops back to the input. We're adding 1, yeah. So if we RAM load, you can see it saving, but we need to load as well when we save there. There's more to it. Want an OR. Let's get rid of this LAN. That's it. I want an OR. I just want to OR when we load or save, like that. But then we also need the, what's the top one? Load. We need an OR here for our loading. I could probably have done that with a 3 input. And the save, like that, when we're saving. Okay, now let's loop around. Let's try that again. RAM load, increments, Yep. If we address save, it sets it to 0. It doesn't want to reset it when we do that, and it's only reset to 0 because there's nothing connected to it yet. We need a second switch connecting up there on save. That. So if we just set data into something weird like 34, then address save will put 34 in there. Address load should put 34 on the output. Yep. That should also put 34 on the output. And this should increment as well as outputting it. So address this one controls a switch to data out, and that probably just wants to go straight through. Is that it? No, that's the RAM controller part done, but it's not the circuit done. We also need to be able to read this for the is it less than 32 check. So in that vein, similar to the other counters, yeah, in that vein, similar to the other counters, we need byte outputs here and here. Let's move these down one. The data is going to be on a different line, so I think, is it data's, when I said data in, that's address data. So address in, address out, and this is data 1 from that, so it's ADR data 1. ADR data 2, RAM address out, RAM save, RAM load. So these M1 switches, which I believe is just as simple as connecting those up there. So yeah, that could have been a 3 input OR there, just connecting those two. And they connect like that. So that in theory is our RAM addresser. I'm just wondering about the slightly weird shape. If I go right one, oh crap. Yeah, I want it there. Oh crap. So what did I delete? Yada. This comes on with that, I believe. This is there. Yeah. Anyway, let's try it. So address load 0 because this goes there. So what's this one? RAM load out, which is this one. This switch is also from here. This one is from load, RAM save, which is there. Yeah. Okay, so put a random address on, address save, address load 1, address load 2. Yep, that doesn't increment. RAM load puts the address on and increments. Number 2 also does the same. RAM save, so choose the other one and increments. So that, yeah, that's correct. So this one, put it in line with that. We then want a new set of buses. Oops, I might want to move these. And then I'm going to need access to the program counter when I do the other one. The program counter is this one. Like that, and then what else goes down there? Don't think I need that yet. Destination, maybe. So let's move these. So like this, they're one over like that. Right. Where's my mouse gone? There we go. Just to make sure these should still work. They don't. Why don't they work? It's greater or equal. Oh, watched state. Oh. Yeah, there you go. It was just to make sure our computer still worked. It didn't, there was a fault. We fixed it. RAM. So we need to also connect in a RAM, which goes like that, and then we want a switch duo. Switch duo here. These are the output, that's the input. Derp. Did I cut something that I didn't mean to? Oh, no I didn't. So purple down there. So this yeah, there, this, like that. So we want RAM address load 1 goes, let's go top down, 1, 2, 3, and then the RAM 1, 2, and save is 3. They just connect straight up like that. This actually wants to connect to there, and the same with that. And then our green one comes across something like that. Let's just start with this. So that's 1, 2, 3 here. So that's that one. Then we can do yellow and the green. So the green, the yellow. That should be RAM connected up. Almost. That should be RAM connected up. But then, yeah. Like that. We actually want to be so there was 1, 2, 3, that's orange, yellow, so I want to be there. Like that, then that can come down one. No, I want to select, that's it. That's it. Right, it's better. So that should be our RAM connected. Let's bring this all the way down. And go across. Like that for now. That should be the RAM connected. But we need to now go into the program and rewrite our code. So we want to add plus I1, I2 in 0 to RAM. Then we don't want to increment that because it should be automatic. We want to check if RAM address is less than 32. If it is, go back to start. Then we want to put 0 in RAM address. That's the break for the first one. We start our second loop where we want to add no. We want to get rid of the add. That one. Add RAM 0 to out. So take what's in RAM, add 0 to it and put it out. Same here. Add 0 to in, store in RAM. Add 0 to RAM and store to out. Basically just go until, copy the RAM address to there. Like that. Then go to start, but that line's probably not going to get used. So that's basically... You'd probably also add a 0 to the RAM address at the start there if you were doing a real computer program, because you don't know what's going to be in the RAM because it's going to be random. But in this game it always starts as a 0, so we can miss it out. So if we run, we're not running. So add what's the in? The in is 1. Add 0 to RAM. RAM is 13, so this one. Sorry, on this one should be lit up, but this one's lit up. In appears to be correct. That one's disabled because it's a absolute. So what's going on here? Oh. Duh. We don't want that 8. We want that 8. So add con is wrong. Which is easy enough to fix. We want a byte output. We also want byte input, and we want to connect we want to connect 1, 2 and 3 across, and then instead of this connect it to 8. And then there. So this connects there with that. Like that. There you go. That should do it. Yeah. It's successfully addressing the correct bit there now. Right. Do that 32 times. Yeah. But it stored 0 every time. So we're not actually storing It's to be like that, doesn't it? We're not actually storing the data in RAM. So you could do that, or it's not going to quite fit anymore because, or you could have another one here that comes on when save is active. That would mean taking all of these raising them to here, then adding byte output with a switch, like that. When save, that's address save, a RAM save. When RAM save is on, things are going to be broken. Because they want to go up one, and this has to go up one. And it's broken now. Circular dependency of the output of a component leads back to its own input. Okay. I guess we'll just do this. It's no big deal. Then this one, and this one, like that. And that worked, but let's run it more step by step so we can actually see it working. So we read in 32 different values in there, and then we output them again. Yeah, and we do that 3 times apparently. So let's pause and run at full speed because we don't need to see it anymore. Next, stack. Probably will give us a slightly better score. I don't think it did. Push and pop now needs to be re-implemented. So to implement the push and pop, we want to add a stack here, like we just did with the RAM there. We're doing the same with a stack, except we don't have a crazy custom controller with a... In fact, let's go in here. This one... No. This one is the RAM address. What the heck did that just connect to? Okay, this one is the RAM. Yeah, this one. Why does it connect to there? It's probably just a graphic bug. And this one connects to there. So I want to go back in here. and the next, yeah, that's RAM. The next address is stack. Did I add stack? Yeah, I see stack. Basically, just like this, what we want is an OR gate. That's basically it. An OR gate on load, which is pop. The custom switch duo on the output there, where I connect them up like that. So this one connects to the top one, this one connects to the bottom one, this one connects to push. The value to get pushed, like the others, just goes like that. Then with a switch duo, that and that. So without the crazy controller, that's what it becomes. So now I edit the program. So what does it want to do? If it is, put it in 0. If it equals 0, do pop. So pop is add I2, which is 0, the stack. Add 0 to the stack, push it throughout. And likewise push is add I2 reg 0 0 to the stack. This one's so simple and easy, so we're just watching this. Yep, it's adding things and popping them off correctly. It is also correctly showing our things here. Let's go back in RAM. So we're watching this to make sure, yeah, the address is working correctly. And finally, for the plan today, we want to add another stack to here, which amazingly didn't cut our yellow wire. Yeah. Let's do it the other way. That's it. Up one. That means we want to get everything here. Also go up one. So that didn't move this. There. And then so this address, and yes, it's going to use the end address, so I'll connect this up now we want to add the C stack, the counter stack. So specifically for addressing, it's going to have a different stack than a data stack. So we're going to re-implement call in a different way. So we will actually want decoder, leg ALU, leg if, ramcon, duo, register plus, switch duo, stackcon. We will actually want a stackcon, but it's a different stackcon. What's this one? Stack data, push, pop, program counter enable. Yeah. So program counter enable, not sure I want it there. Let's put it somewhere at the top like that. So yeah, I want this. Program counter in, data in, we don't need because it's a specialized one now. So let's move this down. There. Let go of the. Let go of the wires for some reason. There. Let's carry. Yeah. Okay. This is the opcode, which we don't want because we're doing differently. So all this opcode jargon stuff disconnected. We still want to keep that bit, but the opcode jargon stuff can get removed. Let's also pull it across here because I don't think we're going to need all the space. We want ins. We want ins. What do we want for ins? We want ins, yeah. We want 2 ins. One of them is the call control in. The other one is the jump in. And so I'm doing this in a different method. So there's jump in, call in, and we actually want to push I want green wires. When they're both true, like that, push. The pop on the other hand, don't need it. So this however simple it looks is our push controller. So adds 4 to the program counter, so that's where we need a loading icon for cursor for some reason. That's where we need that. Then if you notice there's a jump in, so the jump in, I'm going to come this way, that connects to there. Let's pull this across slightly. Oh, whatever. I need to change the leg if to have another bit out connected to 8 there, and this is going to be the call out true. That's yeah. So this goes like that, and what I'm going to do is edit instructions, these ifs here. We're going to add a new bit here, call. And these will remain. Let's copy it again. Call, jump. When it's off, it's a jump. When it's on, it's a call. So you got to if now. If equal jump. If equal call. So we want to go to our tech, turn on jump to make it a call, and kek, CEQ, and likewise TGT, CGT, TGTEQ, C, T less than, call if less than, call if less than or equal to, and call if not equal to. Now technically instead of test, don't want to be jump, so it's jack, but for the sake of rewriting the assembly codes I'm going to leave it as tech. But we should have a new set of these. So instead of call if equal, but since we're not actually testing anything, just put 2 of the same ones and the blanks. Pop will be a little different though. Let's just run it through. So that is push, and jump to func B. It's not at, oh is it? Yeah, there you go. 15 doesn't sound right though. It's supposed to add 4 to it. Yeah. Why is stack counter 11? Why is func B 11? Oh, because pop's not a command. I should put a 0 in there, and that fixes the address. In fact, let's put add. But what we actually want to add to it is add intermediate. Is it I1? Yeah, I1. Add I1. No. 2. Add I2. Add the C stack. Add 0 to the C stack and put it on the program counter. So I'm not going to implement any special return commands. Just going to put C stack into the program counter, and by putting it in there you add 0 to it. So that means I put that on the program counter. We want, once again, switch duo with green and yellow lines connected to them, an OR gate here. Move it up one, where the top line connects to the top one. The bottom line connects to the bottom one. The combined one connects to the pop line, and then top bottom, and that isn't actually going to be used because it's controlled by this instead. So if we open our program again, do step by step. First one pushes 4 because that's the current counter is 0. Next instruction is 4. So we're going to jump to func B, so that put 12 into the program counter and store 4. So we're going to jump to 12, which is here, which is going to jump to A, which is here, which is 8, so it puts 8 in there and pushes 16, which is the next one from this here, into the stack, which it did. So now we're going to be here, which is pop back to the program counter, so that takes our 16 off the C stack and puts it in the program counter, which means we go down here returning to function B. That's pop, which takes our 4 and pops it back to the program counter, so we're going to end up here at 4, which is test to see if 0 equals 0, and if true go to end. End is line 20, so our program counter when I tick wants to go from 4 to 20, which it does. So our next line is here, which is tech again, tech to see if blank equals to blank. If so, go to start, which is 0. So I press next, we go back up to 0. And that should start again. But doing tech instead of an OR, I want an AND, because when I was doing text it was popping onto the pushing onto the stack. So let's try that again. The 4, 16, pop 16, pop 4. Then we're going to jump to 20 and jump to 0 without storing on the stack, which is then going to store 4 and 16 again, and just loop putting on and taking off 4 and 16 while also jumping to 0 and 20 without adding to the stack. So yeah, level is level is complete. Yeah, and that's a better computer. And this is where we start getting into fun programming stuffs. But that's not actually what I want to do. If you noticed, we used this one for call, but that means we also can use it if we're not doing an if. So instead of these, well, that's ALU still, but instead of these being like that, we can extend it to that, so that that specifically means shift right. Yeah. So we go in the leg ALU. Cramped. Yeah. Go down one. Yeah, I can go down one without breaking anything, so that's okay. Right. So it's not just that or that. We also need an and, which I don't think is going to fit without extending up. So before I do that, is it going to break anything if it extends up? No. We're safe. I've got an and in there. Is it an and? Actually, I think it's a second or. Like that. So if this comes on, I want to turn it off. So this fit in here. It's pointless. It's not going to leave enough room. If I want to put that there, like, yeah, it's going to have to be up there. Not want to rotate. Oh, because we put that on. That. Like that. Tight. But that means, for example, you can include other things in there, like the multiplier, stuff like that. But also include like an actual move command. I think what I'm going to do though is put that there, grab this, put it there, but not actually put it there. Just going to get the trio on like that. I can now move this left again. Like that. Let's move that up. Like that. Ta-da! So it just doesn't do anything if that one's on. Likewise, if that's not used anymore. I'm going to leave it on though. Let's have a look at this. Did I delete it from here? No, I left it in. Yeah. So that's the basic ALU. I want to build a second ALU where this one has that, the other one will have a knot in there, and then I can add extra instructions using the lower half, but this is needlessly complicated now because that's not used anymore, which means this, we don't need that, we don't need that, which means we don't need any of that. What's 32? I think we still need the 32, so it becomes that. Actually, no, undo. Slow undo, but it's undoing. Right, so we don't need that. So what's this bit? 16. When 16 is low, yeah. Anyway, what I wanted to do at some point is we run a math instruction and then do a comparison on the result. So we probably need a special line for that, like for example when 16, because I want to use I want to add instructions like a bit test. Now a bit test is basically just put a mask in there, so only one bit in your byte is going to be a 1. And then you only one bit in your byte is going to be a 1. And then you thingy it, what do you call it? Yeah, and them together, and the result will either be 0 if the bit was clear, or some non-zero value if the bit was high. But then you want to branch, which is either a jump or a call, if it was set or it was clear. So basically you want to, you have a, is it equal to 0 or is it not equal to 0? So you're looking at a condition unit similar to not the if like you've got on leg, but a conditional unit like this. Is it equal to 0? Is it not equal to 0? Is it greater than 0? Is it greater than or equal to 0? Etc, etc, etc. Like we are on the Overture computer, so I don't know if I want to use the same condition component, but it'd be similar. And that basically would connect to the output of the ALU. So you're doing your standard maths functions, but then the output connects to the input of this, like that. Yeah, I want to be more complex because we want to connect opcode to this, I think. Or maybe it's just a input that we do from here. Either way, then this will want two outputs again, where one of them connects to here to trigger switching on the destination and upgrading the program counter, and probably also this line, though does that line get turned on from the leg? Yeah, that's just connected to pin 8 basically, so no matter what we're doing this one will turn on. So yeah, so we don't need to repeat the functionality in here. So anyway, it comes in from there, then outputs to here. So that'll probably want to have an OR on it, but this basically wants to turn on when we have so I want to go back into here and replace that with an OR like that. So this one doesn't matter. We want a math regardless. No. Yeah, because that's disabled. Want a math regardless. So duplicate cond2, rename it as leg cond. So our conditions are that's the inverse. It was always this is equal to 0. This one was negative. So if it's negative, it's less than 0. So that's then less than or equal to 0. So in order, that's always equal to 0, less than 0, less than equal to 0. Then you flip it if that one's enabled, so it's never not equal to 0, greater than or equal to 0, then greater than 0, because the opposite of less than or equal to is just greater than. So that's the conditions, and that's all you really need. I want to push that up this way, which means some of these like this I can pull up here, and then I can already just bring that closer. This one I can bring closer, like that. This ones are not going on the input, so I can bring this up here and grab this again and move, and there! Now our leg condition is skinny. Leg cond, like that. So the opcode, let's take that out like that, put it there, because I need some, we want this to come on only if this is off and this is on. So we need a 3 input and we don't want it there. Let's move this one down 1, move this one left 1. Oh. Yeah. Put that there. Put that there. So I'll only come on if, which is maths. That one's maths. Maths wants to be a 0. Put it back there. I know that wants to go up there, but let's put this here first, which is out the way. So when that's off, so when that is on, so yeah. So then you actually want to put that somewhere else, like here-ish, about there. Yeah, I'm experiencing some stuttering. This there. That's the wrong one. of that. Pink. And that. Haha. A bit messy. But then we want an OR gate. Put the OR gate here. Get rid of that. I don't want pink. Like, okay. Why is it like that? Oh well. I can still work with it. So we need to do some things anyway. Right, it does that. And then from here it goes to that. So instead of connecting that straight up there, we want to take it off the ALU plural with an S, ALUs. So I'm going to need a bit more room with that code. So that's as far as I can zoom out. So I want to grab everything up to here and go 1, 2, 3. Is 3 enough? So let's move it back. Let's go 4, 5, 6. Let's move those. So it doesn't quite go in because of them. Just have to reconnect these manually, which should be easy enough. And select and go one more to the right. There you go. So at this point I need 2 switches, a secondary ALU. I'm just going to put in the same one again. It'll probably look something like that and go there. It's that green with magenta. We'll have cancelled that, put them in there, and one of them goes up to there, while the other one cancel. Give me that right down at the bottom. The other one specifically wants to go to there. So then you need some of this opcode logic. Like this. Let's make another custom component, see if it works. It'll probably be easier. A new custom component is the leg destcon. No. Leg destcon. There we go. We want a byte in. Yeah, byte in for opcode. Then we want two 1 bits out. One is to the bus, the other one is to it's the jump controller. One to the bus, one to the jump controller. And don't want purple, pink, whatever, magenta. Is basically just our opcode is that one and that one, but it's not that one. It's not that one and that one. We want to jump, otherwise it's I think it's not to both, innit? It's not that one and not that one for so that's maths, and that's our new decision one. So we add the new custom component, if I can see it. It's leg conned. It's a weirdly shaped thing, okay. Why is that? That's it. Yeah, but let's go back in and just grab everything here and move it into that square. So it should be nice and simple. We take our opcode off our second maths unit, and this one is the bus, outputs to the bus, or outputs it to the jump, the cond. So let's go back to stack. Let's go back to this early one, conditionals. We broke something. That's the program all zeros, look. Why is the program all zeros? That's not normal. Immediate values. Program's all zeros. That's weird. Let's go to on a man. Divide. My program's still there. So my program's working. So let's also check RAM. Stack is building a stack. Push and pop. So everything works, I think. So what we need to do is actually test our thing. If let's go back to if I just realised it was in the same opcode for maths and the condition in the same instruction, which we can't do. All we can really do is a single check. Is it equal to 0 or is it not equal to 0? So if you're adding, for example, all zeros, the jump condition is always going to be always. And if you're subbing, it's also, is it equal to 0? So I can't just use the leg cond. We need to actually program some of them in specifically. Move the AL as if. So yeah, it's not going to work. I mean, this, yeah, it's fine. It just needs more work to it. Yeah, it's crap. Let's just revert back to this. I mean, it's a good principal idea, but I'm gonna remove this for now. No, I didn't want to cut that. Don't need the second leg ALU in there at the moment. So that's connected back up as it was. I'll leave the crazy unfinished instructions. I'll leave the components in there in case I want to try again later. This would go like that. I have to worry about changing that later. In any case, I think I'm done for now. So I'm going to stop the stream